Hi, hola, bonjour, and salam. Welcome back to Blueprint Bazaar. In this video, we are presenting a detailed numerical analysis of an arch dam using ANSYS, where we perform both static structural and steady-state thermal simulations to evaluate the dam's behavior under realistic mechanical and environmental conditions. This analysis helps in understanding how hydrostatic pressure, self-weight, and temperature variations influence the safety, stability, and long-term performance of large dam structures. The study begins with the development of a three-dimensional arch dam geometry in ANSYS. The curved geometry of the arch dam is specifically designed to transfer hydrostatic loads efficiently from the dam body toward the abutments, reducing direct stress on the central section. The foundation is modeled as rigid and fixed, representing strong bedrock conditions, which allows an accurate assessment of load transfer between the dam and the ground. Concrete is selected as the dam material, and both mechanical and thermal properties are defined in detail. Mechanical properties such as Young's modulus, Poisson's ratio, and density are used to capture the structural response, while thermal properties, including thermal conductivity, specific heat capacity, and coefficient of thermal expansion, are assigned to model temperature-induced effects. Accurate material definition is critical for predicting realistic deformation and stress behavior. For the static structural analysis, hydrostatic pressure is applied on the upstream face of the dam, increasing with depth to represent real reservoir conditions. Gravity loading is included to account for the self-weight of the dam structure. Fixed boundary conditions are applied at the base and abutment interfaces. The results obtained from this analysis include total deformation, equivalent von Mises stress distribution, and reaction forces. Higher stress concentrations are generally observed near the base and abutment regions, which are critical zones from a structural safety perspective. A steady-state thermal analysis is then carried out to study the effect of temperature differences across the dam body. Different temperature conditions are applied on the upstream and downstream faces to simulate environmental and seasonal variations. This analysis provides the temperature distribution within the dam and highlights thermal gradients that develop across the structure. These gradients can induce thermal stresses that significantly affect the overall structural response. To capture the combined effect of mechanical and thermal loads, the temperature results from the steady-state thermal analysis are imported into the static structural module. This coupled structural thermal analysis allows thermal strains to act simultaneously with hydrostatic pressure and self-weight. The resulting stress and deformation patterns represent realistic operating conditions that dams experience throughout their service life. Once the coupled structural thermal analysis is applied, we can clearly see how temperature effects interact with mechanical loads throughout the dam structure. The imported temperature results cause thermal expansion and contraction in the concrete, and since the dam is restrained at the foundation and abutments, this thermal movement generates additional stresses inside the dam body. These thermal stresses combine with stresses from hydrostatic pressure and self-weight, creating a more realistic stress condition than structural analysis alone. The results show that temperature changes can noticeably influence stress levels, especially near the base and curved abutment regions where movement is restricted. In some areas, thermal expansion increases overall stress, while in others, it slightly reduces deformation caused by water pressure, depending on the direction of temperature flow. This combined behavior explains why dams may experience cracking or stress concentration even when mechanical loads remain constant. The deformation pattern also becomes more realistic, showing how the dam responds as a single system under real environmental conditions. Seasonal temperature variations, day-night temperature differences, and long-term exposure to environmental changes all play a role in the structural performance of large concrete dams. By performing this coupled analysis, engineers can identify critical zones that may require design improvement, additional reinforcement, or better thermal control measures. This approach also helps in checking whether the dam remains within safe stress limits under combined loading conditions. Overall, the coupled structural thermal analysis provides a practical and realistic understanding of dam behavior during actual operation, making it an essential step for safety evaluation, design validation, and long-term performance assessment of arch dams. In this analysis, the applied loads are defined in a realistic manner to closely represent actual operating conditions of the dam. The hydrostatic pressure on the water side is not applied as a constant value. Instead, a pressure gradient is created using a function in ANSYS. This function allows the pressure to vary with depth, increasing from the top of the reservoir toward the base of the dam, which accurately represents how water pressure behaves in real-life conditions. The pressure load is applied only on the upstream, or water contact, face of the dam, ensuring that the structural response reflects actual reservoir loading. Similarly, temperature is also applied in the form of a gradient rather than a uniform value. The temperature distribution varies from -1 degree Celsius at the top of the dam to 4 degrees Celsius at the bottom, representing realistic thermal conditions caused by environmental exposure and water temperature differences. This temperature gradient creates non-uniform thermal expansion within the dam body, which plays a significant role in stress development when combined with mechanical loads. After applying these loading conditions, the results are obtained by using the imported thermal load within the static structural analysis. This allows the temperature effects to directly influence the structural response of the dam. From this combined analysis, we evaluate key results such as equivalent von Mises stress and total displacement. The total displacement results show that the maximum deformation occurs along the crest of the dam, particularly around the top central region, where the structure experiences the greatest flexibility under combined loading. On the other hand, the stress results reveal that higher von Mises stresses are concentrated near the edges of the dam, especially around the abutments and boundary regions, where structural restraint is highest. This behavior is expected, as the edges resist both mechanical forces and thermal expansion, leading to stress accumulation in these zones. To conclude this analysis, the results clearly show the importance of using a combined static, structural, and steady-state thermal approach when evaluating arch dams. By applying realistic pressure and temperature gradients and importing thermal loads into the structural analysis, we are able to capture the true behavior of the dam under actual operating conditions. The deformation patterns along the chord and the stress concentrations near the edges and abutments provide valuable insight into critical zones that require careful attention during design and assessment. This type of simulation not only improves confidence in structural safety, but also helps engineers make better design decisions for long-term performance and reliability. If you found this analysis useful, don't forget to like the video, share it with others, and subscribe to Blueprint Bazaar for more practical ANSYS simulations, engineering analysis, and real-world CAD-based learning. Thank you for watching, and we'll see you in the next video. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.